facility. We didn't do the tour this year, but maybe we can arrange a tour of their supercomputer stuff there at the Pickle Research Center. So, yep. Lots of cool stuff coming up. As Ian, I think everybody here heard, we do have a subgroup this month. TriNet is sponsoring. It's in the last Wednesday, usually of it.
The last Wednesday this time because last Wednesday is Halloween.
Got it. There you go.
Fourth Wednesday. So.
Yep. Fourth Wednesday this month.
Math is hard.
Yep. So we will do a regular meeting next month. Normally we don't have meetings in December because of the web bash. I think that's still happening. Maybe we might still, who knows? Well, I might start a poll and see if we do a regular meeting instead of the web bash this year. We didn't seem too jazzed up about going to the web bash last year, so may have a December meeting, but obviously we won't have a subgroup until January. So this will be the last one of the year. So, yep. Hope you all can make it out, and thank you again, Ian, for speaking. I think we can get started here.
All right. So I'm Ian Lippman, and we're going to talk about doing fun things with process control and other fun CLI stuff this evening. I gave this presentation over in Portland, and it seemed to be reasonably well received. So let's jump right in here. So what this talk will not be about. This is not a standard, here are the basics of building a CLI application in PHP talk. Realistically, you can use your Symfony CLI tools or Laravel 0 or something like that to build a basic CLI, or find Steve Grunwell's talk on building CLIs, which is amazing, and but that's not what we're going to talk about tonight. We're going to talk about a little bit more advanced stuff. First off, we're going to talk about POSIX signals and how to throw them, catch them, and react to them in your application to potentially turn a Control-C into awakening a zombie from your PHP process. Things that you might have thought that you couldn't actually do in PHP because PHP is a web language and you might need Python or C or something else to be able to catch those signals because they happen asynchronously or what have you. Actually, you can do that in PHP. We'll see how. If you were here in January of last year, this is somewhat rehashed material, but I have a few new things in here because I did a little bit more research in advance of Portland. We're also going to take a look at running things concurrently at the command line, whether that's by forking processes, threading, or using coroutines. You have a few different ways, depending on what extensions you have and what version of PHP you're running, to do multiple things at once. There are a few gotchas and caveats to that we will go into. And finally, as some bonus material, because this is going to be about a 50-minute presentation, give or take, we'll take a look at how to, in the web side of things, background work without necessarily throwing it onto a queue. So, with all of that, I'm going to back up just for a second here. If you want to follow along with this presentation and be distracted with the exact same thing that I have on screen, including following various links there, take a look at this URL. This will get you to the live version of the presentation that will follow along as I present, and that will include links to GitHub repos and that sort of thing, so you can click them rather than copy and pasting. Now, at the bottom of this slide, you'll notice a link to a repo that includes this process control stuff. So if you want to have a look at that, that is there. Any of the code examples that I'm showing here will be there. So, as fair warning, if you decided to show up here rather than the Linux meetup, you're in good company, because this is all primarily Linuxy stuff, or POSIXy stuff anyway. Some of this stuff won't even work on macOS and BSD. So if you're running PHP on Windows, your mileage may vary by a lot. A lot of this stuff just flat out will not work under a non-Unixy OS. You have been warned. Now, the first thing that we'll talk about is signals. So anytime you have a misbehaving process and you say, okay, kill my misbehaving process, which is probably Slack, you send a Unix signal to a given process. In the case of standard kill rather than kill-9, it is Unix signal 6, which is sigterm, which tells the process to get the heck out of Dodge and shut down. Now, if you want to, say, ask the process really nicely, hey, could you maybe interrupt yourself and calm down and hold off and maybe exit, you hit Control-C while it's running in the foreground, and that sends the SIGINT signal, signal 2. Or if you want to shovel the program out of memory, force quit, that is kill-9. All of these and several others are Unix signals, and we're going to use those we're going to override those in the context of a PHP command line application. Again, something that you may not have done before because it's heavy-duty command line-y stuff, but it's actually very much possible. So, in order to do a lot of the things in this presentation, you're going to need the process control extension, PCNTL. This extension will not work under web-based SAPIs or server APIs. It will not work under mod.php. It will not work under PHP FPM. You have to be running PHP at the command line for this to work. So, for example, you can't fork a process from a web worker. That's actually not a thing. So you download and install this extension, you run it at the PHP command line, and then you can do a whole lot of fun things that we mentioned in the rest of this presentation. Any of your functions that are prefixed with PCNTL underscore whatever, those are from this extension, and you will not get those functions unless you have this extension installed, which if you're doing a CLI application, you usually will have it installed, unless you're dealing with Alpine Linux, in which case you have to install every little thing at once, which is fine, but make sure this is installed before trying anything else in this presentation. Now, there is a Docker image, there are actually 2 Docker images associated with this presentation that have these extensions already installed for you, so that you can just grab the Docker image, Docker up, or Docker run, and play with things there. Now, this PCNTL signal thing that I've been talking about, what you're primarily going to be doing in your application is probably listening for those signals. And the way that you do that is you actually tell it, okay, give me a listener, build up a listener, associate that with a callback, and associate that with a callback specific to one or more Unix signals. So in this case, again, we got SIGINT Control-C, we've got sigterm, which is the standard kill. You cannot override kill-9 because the OS just says, you're done, get out of memory. SIGHUP, hang up, etc. There are a few of these that don't necessarily have as well-defined behavior at the OS level, like SIG CONT, SIG user 1, SIG user 2, where you can use those as really quick kind of command line things to communicate to your process while it's running in real time without having some other sort of socket open in order to do various fun things. I actually used that not in PHP but in Python in order to work with basically an echo-like device bouncing between listening mode and speaking mode and a few other things. So in any of these cases, you're going to call PCNTL signal, you're going to tell it which signals you want to listen to, and you're going to provide a callback. Now that callback supports either a single parameter or 2 parameters, or if you really want to, 0 parameters, if you already know which signal that you are being provided. So in the callback case, you're going to get the actual signal number, and as of PHP 7.1 or above, you'll get the SIGInfo T structure that includes the signal number again and a few other pieces of information that at least somewhat vary based on which signal you're getting. Usually it's only a couple additional pieces of information. It may not be terribly useful, but as of PHP 7.1, you have that additional ability to receive that data that all of your normal C programs get when they get signaled. So, one thing that's going to be increasingly important when you're dealing with, say, concurrent processing with forking or signal handling or anything like that is you'll need to know the process ID of the actual command line process that you're running. In order to get that, there is the POSIX way, POSIX get PID, which you need the POSIX extension for, which usually, again, it is installed unless you're running Alpine Linux, in which case you have to install it manually, or get my PID. Now, get my PID is more compatible. That will actually work under Windows if you do PID-related stuff under Windows. POSIX get PID will not, because it requires a POSIX compliant OS, and Windows is not. Now, all of that said, if you want a system call without actually having to shell out to the kill command to send a signal to another process, the POSIX_kill function call will let you do that. It takes the PID of the process that you want to send the signal to and the signal that you want to send, not necessarily a SIG term, and send that on over. So in this way, you can do a little bit of nudging processes around within your application, assuming that your application is running at a user level that is sufficient to mess with other processes. So one thing to note here is you don't want to throw a whole bunch of logic into your signal handler. Usually what you're going to be doing is you'll use the signal handler callback to set a flag. If you're going to keep your application running, you're going to set a flag and then catch that in whatever event loop that you're running or something like that. Or if you're trying to clean up prior to termination of the program, then you can do your cleanup and termination just right there in the callback. But what you don't want to do is say, okay, in my callback, I'm going to move into an entirely different phase of the program, and I'm going to run that entire thing through the callback and through method calls where that callback is in the stack trace, because at least from my experience, once you are one level deep in your callback based on your signal handler, future signals will not actually call that callback again. So make sure you get out of that handler relatively quickly. So there are a few different ways of actually listening for signals. As of PHP 7.1, you have the PCNTL async signals call that. All you have to do is call that and then define your signal callbacks, and everything will work just fine. this is new, and you may or may not want to use it depending on whether there are pieces of your application where you absolutely positively don't want to have signals actually respected in some critical part of the application, where you don't want to be interrupted halfway through a block of logic. If that is the case that you're dealing with, then you want the dispatch signals method that has been available since 5.4. In that case, anytime you call that method, then the application will check to see what signals have been queued up, go ahead and process them by calling any callables, and then moving on. Now, if you want the automated signal handling piece and do not want to use a version of PHP that is not end of life, please don't. But if you really, really are a glutton for punishment, then you can use the single thing that PHP has used declare for since time immemorial, or PHP 4.3, declare ticks equals 1. Again, this is one of the things that declare is used for. The other is declaring strict types, available as of PHP 7.0. This does give you a fair-sized performance penalty in terms of how quickly your application runs, because it's going to be checking on each statement or portion of a statement. Hey, are there any callbacks? Hey, are there any callbacks? Hey, are there any callbacks? Hey, are there any signals? Hey, are there any signals? So it's relatively slow versus using async signals. So you really want to use dispatch or async signals, because at this point, your runtime is going to support either of those as of 7.1. So let's take a look, let's see here, at some code. So let's just start with this one. So in this case, I grabbed the PID of the process, and as soon as I hit Control-C, we're done. No signal handling. If I look at this, you'll see that we've got the, okay, it doesn't show highlighting. Up at the top there, we have the POSIX get PID. Again, get my PID works just as well and is more cross-platform, but I'm running on Linux, so it's fine. And then I'm just sleeping a bit and calling things in a loop. Nothing terribly interesting there. So let's go ahead and look at the slow version of this. So in this case, we are using the PCNTL signal method to say, hey, when somebody hits Control-C, then call this little callable, which says that, well, we close out, we print a little bit of stuff, and then we exit. And right before we actually get into the main body of the application, we declare ticks equals 1, so that it actually tells you, it actually will call that callable. There we go. That's what I wanted. And otherwise, the loop performs the same way it did. So in this case, we run through, and if I hit Control-C, then that happens. So slightly different. Now, let's go to something that has only been available since PHP 5.4. So in this case, we're going to use a full-on signal handler, because any callable will actually work in terms of attaching it to signal handling. In this case, we have the invoke method, magic method. Again, that makes the entire class callable, so we're going to use that. Same sort of deal. But in this case, we're using constructor injection to actually specify the message. We go down here, we assign an instance of this signal handler and do basically the same thing, except you'll notice that I'm using the modulus operator here, or modulo operator, because I have some sensitive code here, and I only want this signal handling to run once I get to the end of a block of lyrics. So I can do that with the PCNTL signal dispatch. So let's see how that works. All right, so we are partway through the loop here. Okay, the loop just passed again, and let's see. Okay, I hit Control C, but it only actually processed this signal after it got to the end of that block of lyrics, which can be useful for, say, if you're having a worker process and you only want Control C to interrupt once a given job is complete, then you dispatch signals and then you tell it, okay, only process signals when a job returns and I'm back in my loop that's about to go and check to see whether a new job is there. So, if you don't actually need to have fine-grained control over when signals are processed, and you actually want the signals to be processed kind of whenever, with some exceptions that we'll see momentarily with signal masking, then you can use this one. So in this case, we're back to using the signal dispatch callable as a closure. And you'll notice that, okay, in that case, all right, so I'm actually redefining the closure here. First, I define it as something that just uses what we did before, and then I overwrite that with a new signal handler, and there's only one signal handler for a given signal at a time, and that signal handler actually takes the second parameter that is available as of PHP 7.1. Now, while these signals are processed asynchronously, they are still handled in process. So you'll actually end up blocking the main execution thread when you're doing this processing, so you can see that when we actually run this in the sleep call actually does fire. So once again, we are running through the lyrics of this Beatles song that will never leave your head now. Control C that, and you see that SIGINFO T structure that is available as of PHP 7.1 on any signal handling callback. So those are the various ways of actually reacting to signals as they come in. Again, Control C is the really easy one to demonstrate. You can do this with a number of other signals. So let's jump back to the slides.
Before you do, I have a question. So I ran the PHP.
May I take questions after I get through the signals portion?
Sure.
Thanks. So the reason I mentioned that is there are certain things that I may answer your questions prior to finishing the end of this part of the presentation. So if you still have the question at the end of it, go have at it. So the next piece is, let's say you have done async signals, but you want to say, well, actually, I don't want to accept Control C while I'm in a sensitive portion of my code. So that's when masking signals comes in. This is another process control function. You call it, and you can either add signals to the mask, you can remove signals from the mask, or you can swap out one mask for another. What masking does is it queues up signals, and then when you remove the mask, or you wait for the signal, which we'll see in the next slide, then all of those signals will fire at that point. So you can say, actually, ignore Control C's until I get beyond this sensitive portion of the code, so I'm not, breaking a database transaction or something like that, or a MongoDB, whatever. I guess they have transactions now. And so we can say, okay, let's wait until we finish the transaction and then process any signals that we have outstanding by this sig proc mask function. Now, this still requires you to dispatch signals, at least under normal operation. So you still will need to do your async or your dispatch or your ticks in order to pick up that signals are happening at all. The only thing that masking does is it says, hold on, don't tell the application that this sig term or this sig user one or this sig int came in until we unmask. So let's take a look at what that looks like. So in this case, I'm using async signals here because I'm using PHP 7.2, so that's a thing. Side note, PHP 7.3 RC like 3 or 4 came out today, as well as other versions, other newer versions of PHP. Make sure to upgrade. I believe there's some security fixes in there. So you've got, we're blocking Control C here because important things. We are masking that and then sleeping for 10 seconds because I couldn't think of something actually important to do because mining Monero, I don't know what the PHP library for that is. And then after 10 seconds, we say, you know what? If you hit Control C, let's go ahead and process that signal now. If you haven't, then we're going to hang around and we'll still accept signals, but we're not going to materialize the signal out of thin air if you didn't actually hit Control C. One thing to note here is this only blocks Control C. SIGTERM will still shut down the application. So let's actually execute this. So I'm not going to hit Control C or anything right now. I'm just going to let it run all the way through. And 10 seconds. Actually, I lied. I'm hitting Control C. So in that case, it caught Control C and it exited because I did it after it unmasked. So let's see what happens. Okay, I'm going to hit Control C now, and nothing's going to happen because the signal was masked until the point that it says, okay, let's oh, there's a Control C there. Let's go ahead and exit. So you have fine-grained control, even if you're using async signals, you have fine-grained control on when you process a given signal by masking that signal. So here's another fun thing you can do with signals. You can actually wait on them. You can say, hey, hold on, wait until we get a Control C or a sig user one or what have you. And that doesn't actually require signal dispatching. You don't have to do ticks, you don't have to do async, you don't have to do signal dispatch because your application is blocking until such time as that signal comes in. So in that case, we can either wait until the signal comes in indefinitely, or we can wait with a timeout and then move on. Now, in this particular case, it will actually consume signals that were previously masked. So if you're saying, hey, wait for this signal to come in and you already masked it, well, it's going to consume from that mask. It's going to override the mask because there was a Control C there and you're explicitly waiting for that. So one thing to note here is this will not work on macOS. This will not work on BSD. This will work on Linux, and hopefully you're running stuff on Linux and prod. If you're running NetBSD or FreeBSD and prod, that's cool. If you're running macOS and prod, then why? But that's WaitPid, or sorry, not WaitPid. That is waiting on signals. So let's see an example of that. And in this case, I believe I'm going to have to open a couple of windows here. So in this case, we have this. We're going to wait for sig continue. Except note that the callback while you have to declare that the callback is actually there, it's not going to actually run when you're waiting for a signal. When you wait for a signal and the signal comes in, then it's just going to continue executing and return the signal and not execute your callback logic. So we go through here, and if you try to run this on Mac OS, those functions don't exist, so you won't get the ability to wait. And we are waiting for 5.12 seconds there. We are waiting indefinitely on the other one. So in this case, all right, so it's going to wait for up to 5.12 seconds, and all right, it's done waiting, and it did not get anything back, so it returned -1. So now I'm going to open up a new tab that you can't see, and that is PID, that number. Copy that. Kill-sig, SIG, CONT, and I PID, and there we go. So that is the structure that it spits out when it gets the signal. So in this case, let's see if I have fast fingers here. So that's 5.12 seconds, and that is 836. Nope, not fast enough. There we go. And there we go. All right, so that is in the case of waiting on signals. Jumping back to our lovely presentation here. So we have the process control alarm function. This will fire off an alarm in X number of seconds. That will be handled via whatever signal processing you have, and you'll need to attach a handler to the special SIG alarm signal. Now, you can only have one of these outstanding at a time, and you, of course, only have one handler that is associated with SIG alarm. So let's see, and if the script is sleeping, then it's going to interrupt the sleep. So if we go back here, all right, I wonder whether I'm still in Do Not Disturb mode. No, I'm not. Okay. That means you might actually be able to hear that terminal bell if I turn this up. So it's setting alarm, and we'll set it for 10 seconds, let's say, and then alarm, and note that the sleep down there is really long, so it's going to alarm in a few seconds, in which case we'll move on from these particular examples. So normally it would do the terminal bell thing, but I think by default, the Ubuntu terminal turns off the terminal bell, so it doesn't get really annoying. So with all of that said, let's put all these things together and build a zombie that if you leave it alone long enough, then it will just die in its sleep. If you don't leave it alone long enough and you Control-C it, then it starts screaming at you. And then you kill it with the sigterm command, and it dies. So let's see what that code looks like. So we're using POSIX to get PID again because I don't care about anything other than Linux for the purposes of this demonstration. And we're sleeping, and if we sleep for 60 seconds, then the zombie dies in its sleep. If And note here that I use that convention of exiting from the signal handler as quickly as possible so that I can still accept additional signals. So I have this is awake flag to determine whether the zombie is actually awake. So note here that sigterm is wired up differently than sigint, and sigint will wake up the zombie and have it yelling for brains if we control C while it's sleeping. Point being, don't necessarily interrupt a zombie. And this sig alarm is what we're going to use for process flow to make sure that after 60 seconds, the zombie either dies in its sleep or dies while shouting brains. And because we're using PHP 7.1 here, or rather 7.2, async signals actually work. So, with all of that said, I'm getting really impatient here, so it's now yelling at me, brains, brains, brains. Let me go ahead and sigterm that. That process ID is 8927. And there we go. So, by contrast, if I do a sigterm right now, then let's see what the process ID is there. It's 8934. So, point being, you have a few different processes or a few different ways that you can interact with this zombie, and you probably don't want to use Control-C to interact with it because you try to interrupt it and it wakes up, and then it starts yelling brains, and then you've got an angry zombie on your hands. So, now, that marks the end of this section of the presentation. Paul, what was your question?
So with when I run async.php, after I control C it, it's like one Mississippi, two Mississippi before I get the command, before I get like the prompt again. But if I run the other one,
So if you look inside async, you'll notice there's a sleep inside the signal handler. There's actually, it's a sleep 1. So that's why there's a wait before you get the prompt back. If you're looking at the dispatch, then it only receives signals every so often, in which case it'll keep executing until it's like, okay, I want to listen for signals now. Oh, hey, there's a signal. And then it'll clear out and drop to your prompt without a sleep because there was no sleep in there. Does that answer your question?
yeah, I did see that sleep one. I'm not really sure what's there.
Because I put it there? Because I wanted to show that the sleep actually the execution of that async signal handler still happens in the primary process. It's not like running in a separate thread or anything.
Oh, gotcha, yeah.
So keep that in mind, that signals do not magically make your application concurrent. The things that we're talking about making your application concurrent are, well, sorry, I have a race condition there. Let me fix that. There we go. So we're going to talk about concurrency in PHP command line applications because that's actually a thing, despite the fact that people are like, well, PHP can't do concurrent stuff. It's like, aside from the fact that you can fill up all your CPU cores serving concurrent web requests because one request per one process or one thread if you're brave enough to do the threaded npm on Apache, you can actually at the command line do multiprocessing rather by forking or by pthreads or a number of other things. So the first thing that will actually work anywhere PCNTL is installed and will work on non-thread safe versions of PHP is the PCNTL fork command. What this will do is it will copy the memory of your process over into a different memory space and start executing two versions of the process at the same time from the point at which you hit fork. And you'll be able to tell the difference by the return value of PCNTL fork. Whether that is true, in which case you're in the child process, or the PID of the parent process, or -1 in the case of, yep, it's -1. And sorry, it's not true, it is 0. So you don't want to actually just do a falsy check on this, because the falsy check is like, okay, well, that means you're in the child, but at which point you probably didn't check to see whether the fork errored out. So you really want to use a switch statement to confirm that your process actually successfully forked. Now, one thing to note here is if you fork a process and you're using a database connection, then that database connection, you only want to use that in a single process or a single thread, so you need to create another one. You need to shell out the old one, because the old one, at least in the child process, the old one is going to give you weird consistency issues, i.e. not work at all if you try to use it in your child process. We'll see exactly what you want to do for that momentarily. One other thing you want to do is, since child processes generally don't outlive the parent process, you want to wait until child processes are complete before closing out your parent process, and you do that via PCNTL wait PID. So you want to keep track of the process IDs of the children that you forked out, that you spawned, because you're going to need those later to say, hey, wait until all of the child processes have actually finished executing. So this is a real-world example of a case where I needed to hydrate a whole bunch of tables, and I wanted to do them concurrently because that was faster than doing them one at a time in a loop. To do that, I have forked a whole bunch of processes, one per table. If I was in the forked process, then I went ahead and hydrated the table and then exited as quickly as I could, so I didn't have code running in parallel that shouldn't have been. See the highlighted, yep. See the yellow highlighted lines in there. And then if we make it past that exit, which is on the branch of, oh, hey, I'm in the child process. If we make it past that exit, then we're in the parent process, and then we check over all of the child processes and say, okay, wait until each one successively is complete. Now you can do some more fancy stuff to check liveness so that you're making better use of your time in the parent process. If some child processes finish a lot earlier than others, and then you can throw more child processes on there and that sort of thing. But that sort of flow control wasn't really necessary for the project that I was working on, because you only had, I think, half dozen or 8 or so tables that I needed to hydrate, and just firing off all the processes at once was sufficient. So, let me see if this is, okay, that is, so let's actually look at another example here. So we are going to, since this was originally built for Cascadia PHP, we are going to look at Cascadia, we're going to look at Longhorn, and we're going to look at PHP.NET. We're going to pull those down, and while there are multiple fun ways of doing async concurrent web requests, we are going to fork processes to do it in this case. We have this case statement here, as I mentioned in the example. We can see, okay, we're in the child, we're in the parent, or we are or something failed, and we execute things as needed, write stuff to files, and then read files from the parent. So let's see what that looks like. So in each of those cases, we executed stuff in whatever order they executed in. We got the responses back, and those files were written. So if we, and the waitpid call will actually give you back the exit code of the process. So you can see whether the process exited successfully or with an error or what have you. So, and I have no idea why we're taking a full 1 3/4 seconds to load our own conference website. That's weird. So, pthreads. Now, this one is a PHP extension that you probably don't have installed because you're probably not using the Zend ThreadSafe or ZTS version of PHP, which it took a few tries, but as of PHP 7.2, they finally got it right, and Zend ThreadSafe is actually, well, ThreadSafe. So it's pretty reliable to work with this at this point. That said, there are some extensions like Locale that are built out in a non-ThreadSafe way, and if you're using something like Locale and you have different threads doing different things and using different locales, then stuff is going to break, and that's one of the reasons why I would venture to guess that the vast majority of PHP installs out there are non-thread safe. But if you want to use threads in PHP, you can totally do that, and the pthreads extension provides some relatively high-level primitives for safely doing threaded communication. Being able to wait for a process or a thread to complete some action, or reusing a thread to perform some level of work is all built into the pthreads extension. As fair warning, while pthreads has a fair number of examples, the documentation leaves something to be desired. So you're really going to have to dig in and look at examples. Fortunately, in addition to the ones that are on the pthreads repo, we have a few of our own. So let's take a look at those. So in this case, what I'm going to have to do is build out a Docker container with the Zend ThreadSafe version of PHP in order to actually run this. There is a Docker file in the repo for this specifically, so you can do that, but just keep that in mind that chances are if you have a version of PHP installed locally, it will not support this. Not only because you don't have the ZTS version of PHP, but also because I had to download the master version of pthreads from GitHub and compile it manually to get this to work. It's not actually that difficult thanks to Docker's Docker Hub PHP image set, but it's still something to keep in mind. So we go down here and we have what I've done here is shamelessly copy the pthreads code for being able to execute a callable or a closure in another thread, which, as long as you're using threaded data structures, you can share things between threads. Keep in mind, if you're not using thread-safe data structures, which pthreads provides you, then pthreads will serialize your object to pass it between threads. So if you have, say, a closure in there or whatever, then that serialization is not going to work. So fair amount of boilerplate here just to get a callable to run, but once you get all that stuff done, we'll call each of those, one being a thread that waits 10 seconds and one being something that actually gets the Cascadia PHP speaker list. And each of those is in a child thread. So we can actually wait on the main thread and maybe do something useful in the meantime because we're actually doing some multiprocessing here. So let's see here. If I want to run this inside Docker, we want all right. So I had a bunch of layers cached, so that went pretty quickly. And then let's look at the README again and see what we need to do next. All right, I actually got that right. And it's got the speaker list result with the first few lines there, and then it finished sleeping. So we actually had three things going on at once using threads, not using fork, not using multiple processes, but actually using threads in PHP and doing it in a relatively safe way. So you could do an entire presentation on pthreads. I'm not going to. It's a really fun thing, and you should check it out. But given that involves compiling something from source off of a GitHub repo rather than, say, Peckle, I don't blame you if you don't want to put it into production. Yep.
So you showed an example running at CLI.
Yes.
What about pthreads from
You,
through a web request?
what you would have to do there is either have a CLI-based queue worker or run your entire application via a CLI-based web server. So something like AMP HTTP server or one of a few others. But as with any of the other pieces like PCNTL in this, you cannot do multi-threaded or you cannot do PCNTL calls within a WebSAPI. So modphp and FPM, you're not going to do background processing that way. If you want to do concurrent PHP, it has to be at the command line. So AMP, so I said that pthreads was relatively poorly documented. Basically all of AMP's Hacktoberfest issues are, will somebody, for the love of all it is, wholly document this library? The examples are reasonably good, but in terms of non-example documentation for a lot of AMP stuff, at least a month ago was kind of a trough in terms of how much documentation there was. I could swear that there was more documentation at one point and then they removed all of it because they reworked a whole bunch of stuff. That said, the cool thing about AMP is it allows you to use coroutines and the yield keyword in a similar way to the way you use async and await in JavaScript, where instead of async and await, you have a generator or a function that ends up being a generator would be your async function, and then your await keyword gets replaced with the yield keyword to say, hey, get back to me when this promise resolves, and in the meantime, do something else useful because we are executing in node style where it's a single process per that's multiplexing requests on top of that. Now, all that said, you can use that same structure in order to do multiprocessing, where you're yielding in and waiting for messages going back and forth between various threads. So this will actually sit on top of either forking processes or threads, depending on whether you have pthreads installed. So, and it also integrates and provides a little bit better API over various extensions like the shared memory extension and a few others, where the defaults are kind of ugly pseudo namespace PHP functions that are a bit difficult to do correctly without shooting yourself in the foot. So if we go over here, in this case, we're going to use AMP to have a bunch of blocking tasks. Now those are going to get farmed out depending on how I execute this, either to pthreads based threads or to processes via fork. AMP under the covers decides which is actually supported and uses the most efficient one, which if you have pthreads, it will use that. Likewise, we have something that's waiting every 500 milliseconds saying, hey, the parent process is still doing its own thing, while the child processes are actually blocking while calling file get contents on those sites. So we have this yield here because, again, we are using generators to deal with moving tasks around. And we're wrapping up all the promises in this yield from to say, hey, make sure that everything is complete, resolve all the promises, and then get back to me with results. So, and then finally we shut down the entire worker pool. So I believe that will actually work. Yep, that definitely works at the command line directly on the system here that's non-thread safe. Alternately, let's see if it works in our pthread space container. And it does. So AMP actually abstracts out the threaded or multiprocessing fork-based variants of executing tasks in parallel on PHP. So let's say we have a process that we don't have control over that is just going to block, and we want to execute that out of band. Now we're getting into bonus content here where this can actually, to some extent, work whether you're on a web SAPI or whether you're at the command line. So let's say we have this sleep and write thing here, and we want to run that backgrounded somehow. One good way to do that is the Symphony process component. What Symphony process will let you do is start running a process asynchronously, and as long as, and since this is a parent process, child process thing, you still have to, unless you do additional special stuff like no-hup or something like that, you still have to have your parent process survive until your child process is complete. But you have the ability to fire off multiple processes, check back to see whether they've completed yet, check back to see what the return codes are, and have an all-in-all better API for executing processes than a standard exec, which is going to block, or wait PID or something like that. So let's look at process.php. So in this case, we're finally actually including a library that's not built into the heart of PHP or is an extension. In this case, Thank you for reminding me. Okay, there we go. So we've got Symphony process component there. We have a few different files here. Again, we're going to write to various files there, and we'll see that that actually works in just a second. In each one of those, we're waiting for X number of seconds, and then we're writing to the file. That's built into what we're going to consider a black box, so that sleep and write command. And what we're doing here is, instead of the process run method that is built into Symphony process, we are using the process start method, which will start the process and run it asynchronously until we say, hey, what's the process doing over there? Or we exit the parent process. So let's see what happens here. All right. So in that case, we got the processes out, and we have test 1, 2, and 3, and they were saved out there. So yep, okay. We have the expected values there. So that is the Symphony process component, and it's actually pretty well documented. And as with a lot of the Symphony components, the API makes sense, and the inner workings of it are a little bit to digest, because the commands, the underlying methods that it's using, such as proc open, are not the most user-friendly things in the world. But you can definitely dig into the source code and see how they execute those things, but you don't really necessarily need to, because they've got a pretty nice API on top of it. So if you want to process something in the background in request, there are a few ways to do it. Again, you should probably use a queue, but one way to do it is this lovely thing that you have access to if you run using Nginx or Apache with PHP FPM, namely fast CGI finish request. Now what this does is it's still going to tie up your FPM worker until everything gets complete, but it'll allow you to actually flush out whatever response that you've already echoed out, whatever headers that you've already sent. It closes off standard out, it closes off standard error. Note, it closes off standard errors, so if you are logging to standard errors, say in a Docker container, because you're not multiplexing things quite correctly, oh wait, that's me, then you've just lost error log. So you have to keep that in mind, and you have to make sure that either your FPM errors are going to the correct place, or generally you're not passing them back over fast CGI, because that fast CGI connection is closed. But if you do that, then you can end up with, structuring your application pretty easily to queue up tasks that happen after your request closes. This is what the Symphony terminate method does. This is what, as a result, the terminable middleware in Laravel and Lumen applications do, where you can set stuff to happen after the request is closed, and the response goes out, and there's no actual execution time penalty for this, unlike, say, throwing something on SQS. So if you have, say, a 20 millisecond request plus 100 milliseconds of background processing, or 200 milliseconds of background processing, you can go from a total time to response from 120 to 220 milliseconds to 20 milliseconds plus the worker being used for another 100 or 200. I'm actually using this as of a week or 2 or 3 ago in a production context where I didn't feel like adding a full-on queue, and I wanted stuff to execute after the response has gone back to the end user, because the API that I'm interacting with is glacially slow in certain cases. Doesn't really matter to me if my FPM worker is sitting there for an extra 10, 20, 30, 40 seconds if I've already handed the response back to the user in 500 milliseconds. So this is actually really handy. I'm not going to, well, let's see here. There's a version of the raffle app that has these changes in it. Let's see if I can do a quick get diff to show you them. All right, so there's actually not a whole lot different between the version of this application with the fast CGI finish request method in there and the normal one. Now, as a kind of way to show that this is actually working, the fast CGI finish request kind of adding that all of the SMS calls to Twilio or Nexmo are actually happening synchronously, and so they're happening one after the other. So if it takes 150 milliseconds to make a call to Twilio, that 150 milliseconds multiplied by how many ever people are actually submitting to the raffle, that's going to add up to an amount of time that is actually not negligible. Well, if we push that to after the request completes, then you really don't notice it, and the response comes back in however many milliseconds. I think it's like 20 or 30 or 40, and then all of the additional work, even though it's not actually concurrent or asynchronous, strictly speaking, is happening in the background. So what we're doing here is we have a little quick job queue thing that I can throw closures onto, and then it'll execute the closures when I tell it to. And then one thing that I do here is I push the container, I push the SMS bits that, there's a dummy version of this that will just log things out. And since standard error gets closed as soon as I call fast CGI finish request, it appears as though that dummy SMS sender stops working. So I've intentionally said, actually just keep that outside of the job loop, still have that happen synchronously. But everything else, instead of executing immediately, go ahead and queue up that SMS send, and we'll get to it later. So this deferred SMS thing is just a shim around another SMS provider that instead of executing that SMS provider immediately, it queues it up and then executes it later. Conforms to the exact same interface because there's not much of an interface. So, like I said, not much of an interface. So what this looks like in the actual execution of the application. Go ahead and call that. And then at the very end there, if fast CGI finish request exists, then go ahead and flush out the buffer and in that fast CGI connection, let the result go to the browser, and then execute the background processing tasks. Now, one cool thing about PHP 7 and above is if you have exceptions that happen after the response ends, then you can actually do something sane with them by in your job queue loop there, doing a try catch on throwable, and then logging out those exceptions as needed, which is what I actually do in that production context that I mentioned earlier. So that way I still get my error reporting, et cetera, when I would normally get a 500, but since that response is already out there, there's no 500 to give because the response has already finished processing. So the other way of handling asynchronous processing, and this is for cases where you actually want the worker to exit out and kind of do its own thing, is no hub or no hang up, where that effectively runs a process detached. In order to run actually detached and not have to wait for it, you have to pipe all your output and standard error and all that sort of thing to dev null. But if you do that, then you can have something that returns immediately, and the process that you no-hubbed will actually outlive the parent process if it needs to. One catch with this is this doesn't actually work properly under the PHP built-in web server. You're going to want to use this in the context of either PHP FPM or mod PHP. And by doesn't work properly, I mean that no-hub, instead of actually executing and going into the background, will still block your response if being used with the PHP built-in web server, because the built-in web server it can only serve a single concurrent web request. It'll just kind of sit there with a response mostly sent, but not all the way. So just keep in mind, if you're testing with a built-in web server and you're wondering why no-hub doesn't work correctly, that's why. It's expected behavior. So with all that said, depending on how fast your queuing system is, you may want to throw this stuff onto a queue rather than trying to execute it using these little tricks. With that said, if your queue is, for example, Amazon SQS, where it's relatively heavy to throw stuff onto a queue, it actually makes a lot more sense to tie up an FPM worker doing a little bit of background processing rather than throwing 5 or 10 jobs onto a queue and then having to pull them off manually, making HTTP calls later. If you're dealing with a Redis-based queue or something that's a lot faster, then the balance between throwing stuff on a queue versus using fast CGI finish request and kind of backgrounding that last little bit of logic is going to be different. But from what I've seen, there are a few folks like Help Scout use this fast CGI finish request. There was another presenter at Cascadia who was going through, like, here's how we optimized all of our stuff for a pretty high level of traffic, and they use fast CGI finish request pretty heavily. DMV.org uses fast CGI finish request relatively heavily. It's this little hidden gem that if you're using a fast CGI based worker system for your PHP stuff, then it's a nice little zero cost, as long as you can move your logic from over here to down here, make everything faster from the perspective of the user button without using additional resources. So with all of that, that basically timed perfectly.
They loved it.
That this is my information. Okay, good. I removed the joined in link for the Cascadia PHP thing because as much as I would like additional reviews on there to counteract Jessica Mauerhand's 4-star review, it's fine. I don't take it personally. That the top link is a link to this slideshow. I will switch it off of live thou shalt follow me at every slide mode and into the standard you can look at any slide in any order mode. Both the raffle repo and the various scripts that I showed here are at those GitHub links. If you want to look at other random GitHub stuff, that's my GitHub. If you want to look at other random Twitter stuff, fortunately, I mostly stayed out of today's PHP sandwich debate, just because people like arguing about sandwich taxonomy, apparently. There's my Twitter. And with that, are there any questions? Go ahead.